A logistic function is usually a model for modeling growth for a population. It is a common S-shaped curve with an equation like so, where the colored letters C, A, and K are constants. As an example, I made up this particular equation where 10 will be the constant C and 4 is going to be the constant 4 and K is going to be the constant 0.6. Note the minus sign is not part of the constant. If I were to draw this function, it would look like this graph, where if you notice 10 represents the upper limit. It means that the function won't grow beyond the level of 10. This is usually known as the asymptote. With these functions, the x-axis usually represents time, and therefore we usually take it from 0. So that if we want to calculate the value of the function at time is equal to 0, we just have to make the x equals 0 and calculate the result. Since 0.6 times 0 is 0 and e to the minus 0 is equal to 1, we are left with only 1 plus 4. And you can see that this is reflected in the value 2 here. This can be very quickly calculated by, for the y value, making the c equals to 10. So it will be c over 1 plus a for the y value, and of course 0 for the x value. Point of inflection is the point between the concave part of the graph and the convex part of the graph. It is the part of the graph where the gradient is the steepest, and it will be right here. And notice that it will be halfway in with the population above and halfway with the population below. And it is easy enough to find the y value or the function value of this point, because all it will be is c over 2. C over 2, halfway. So far, our knowledge of the constants in the equation allowed us to calculate a lot of values. But with the point of inflection, now we need the x value. So is there an easy way of looking at that equation and calculating that x value? Well, let's look at the long way first. We know that we are told that there is a point of inflection at x if the double derivative at that point is going to be 0 and the sign of that double derivative changes at that point. So before we get down to the double derivative, we need to go and find out the first derivative, which is the gradient of this function. I will use the general expression of this equation to help me find the derivative. First, I'll rearrange this equation so everything is in the numerator. So to find the derivative of this, now I'm going to take that minus 1 exponent and move it out to the front, times this by c, and then rewrite this whole thing again. The exponent will be now minus 2. And this is a chain reaction, so I'm going to have to now derive this part, followed by the minus k. Now, since they're all multiples of each other, that minus and that minus multiplied together will give me a plus. And I'll just make a little rearrangement and put that k in front here. In fact, I think I'll put all the constants to the front, the a and the k here. I'll just rewrite this one more way, and I'll put that e to the minus kx in front over here. Can you see if I wanted to differentiate it, I'm going to use the product rule here. So that u dash will be equal to, which is really going to be minus CA k squared. e to the minus k. And v is going to equal to, and v dash is going to be minus 2, and I still need to differentiate e. So there'll be a k over here. Minus k and minus 2 will be, and so now we're just going to multiply these two together and add them to these two together. Let's remind ourselves of what we were trying to do. Well, it says that there's a point of inflection at x if f double dash is 0. So we need to now make our equation equal to 0. Now this allows me to move all of this to the left-hand side. This way I can see that I can cross out the c, and I can cross out the a's, and I can cross out the k squareds, and I can cross out the e minus kx, and all I'm left with is a little bit more in rearrangements over here, and we'll get, so by exchanging the numerator with the denominator, I'll get rid of the negative exponents. And remember, we want to find the value of x, so in that case, a bit of rearranging again. I think I will ln both sides, which will give me, according to the laws, and of course ln e is just 1, which leaves me with minus, and I've moved the minus to the right hand side, which means I can now do the reciprocal of 1 over a. And lastly, I'll separate the k from the x, and that will be ln a over k. And so you can see that a is a constant and k is a constant, and instead of us going through this extensive rearrangements, manipulations, we know that x is just ln a over k. And so to answer your question above, as we go above, we now know that the value of x here is ln a over k. And in our case, in our example, x is going to be ln 4 over 0.6. So our point of inflection, POI, is ln a over k c over 2. These are the coordinates of the point of inflection. If you found this helpful, then please like it and subscribe to my videos, which will be coming soon. I'm happy to take questions on any mathematical problems that you have, and I'll make some more videos. Please send them through to my email.